Hi everyone, and welcome to another video in the motion series in which we're going to look at motion equations for the first time. I've got 4 of the motion equations written at the top left. The first one connects VU, A and T, the second one SU, T and A, the third one VU, A and S, and the fourth one SU, V and T. Depending on which variables you're given in the question, you will use a different one of these motion formulae. And the final formula I'm going to introduce, you don't see it all the time, but it's S is equal to VT, take a half AT squared, which I normally don't use. I'm not sure if I don't use it because it's uncommon or it's unnecessary. But we won't be using it in any of the videos I'm doing. You may find you can use it in a question you find yourself. So the example question, which we are going to be looking at now, involves a sledder originally travelling with an initial velocity, so we'll use a u there, since the u represents the initial velocity in our motion equations, at 5 meters per second, taking the positive velocity and acceleration to be in that direction there. And then this sledder hits, we'll say, rough snow and skids to a stop over 20 meters. So once the sledder reaches this point here, it begins to decelerate or have negative acceleration. And then over that 20 meters comes to a complete stop with constant acceleration. I'll jot that down now. Constant acceleration. And when I say acceleration, I mean negative acceleration, which in everyday life we'd probably refer to as deceleration. The 2 questions I'm going to ask are, first of all, what time does he take to stop? What time does he take to stop? And secondly, what was that acceleration? So let's ask ourselves first of all which variables we've been given. We know he comes to rest here. So the final velocity is going to be 0 meters per second. So we have V, U, we have the displacement during which the acceleration is taking place. And we're looking for T. So can we find a formula up here which has V, U, S and T in it? I think this one here is the one we're looking for. There's V, there's U, there's S and there's T. So we want to get T by itself. I mean, if you were a physics student with an unorthodox method of working it out, you could leave T in the equation there and simply start dividing by these individual values. But since we're smart physics students, we're going to rearrange that formula to get T by itself, so we can just plug into the calculator straight away the sums we want to solve. So let's get T by itself. We start out with S equals a half U plus V times T. Therefore 2S is equal to U plus V times T. Therefore 2S over U plus V is equal to T. Let's pop in our real values now. That's equal to 2. Well, S is equal to 20. And U plus V is equal to 5. So 2 times 20 over 5 is equal to 2 times 20 over 5. That's equal to 2 times 4, or 8 meters. Whoops, sorry, 8 seconds. 8 seconds, since we've got time by itself here. So the amount of time it takes for this sledder to come to a stop after meeting this rough ice is 8 seconds. T is equal to 8. Always remember to deal with meters per second squared, and seconds when you're using these formulae here. They're all in metric units. The second question, what was that acceleration? we had the variables u, v, and s from the beginning. T is the one we worked out. Some people would suggest that since we have v, u, and t, we can use this formula here to work out the acceleration. I agree that it can be done. However, we all make mistakes in our working. It's possible that in a stressful situation, your answer to this first question may not be correct. In fact, if you go through the whole exam, it's very likely you will have some incorrect answers. Therefore, I think it's best, if we want to find the acceleration, to use the formula up here that doesn't rely on a result we've just found. Instead, we're going to use a formula that has v, u, s, and a in it, which would be this one here. That way, we're only relying on the figures we've been given by the question, not the figures we've worked out for ourselves. So we have v squared equals u squared plus 2as. We want to get a by itself. So v squared is equal to u squared plus 2as. So v squared take away u squared all over 2s is equal to a. Just skipping the intermediate step there. So we have 0 squared, since v equals 0, take away 5 squared over 2 times 20 is equal to negative 25 over 2 divided by 20, which comes to, on the calculator, negative 5 on 8 meters per second squared. Why did we get a negative acceleration? Well, it's because the initial velocity was 5 in the positive direction and it became smaller. So the change in velocity was negative, and therefore the acceleration we got was negative. The one bonus question I'm going to throw in at the end here is to ask if we maintain this same acceleration, because the acceleration is mainly determined by the friction of the sled on the snow. So that is our set in stone acceleration. A is equal to negative 5 on 8 meters per second squared. If we had that same acceleration, but the sled was now travelling, the sled had been travelling, not at 5 meters per second, but now at 6 meters per second, so 1 meter per second more. Let's find out the stopping distance it has to take now. So we have A, we have V, we have U, but we want to find S here. Let's use this same formula here. So we V squared take away U squared all over 2A is equal to S. This now comes to 0 squared take away U is now 6 meters per second, so 6 squared divided by 2, and that was negative 5 on 8 for A. And that comes to negative 6 squared divided by 2 times negative 0.625 or negative 5/8, which is 28.8 meters stopping distance. Recall, the stopping distance when the sled had been travelling at 5 meters per second was 20 meters. But by simply adding on an extra meter per second to the velocity, we've increased the stopping distance by almost 50% again, adding on almost another 10 meters to the stopping distance. This is the principle behind road safety's wipe off 5 advertisements. Because if you wipe off 5 kilometers an hour, the stopping distance that you can reduce the reduction in the stopping distance actually increases quite dramatically. So you can save lives by reducing your stopping distance. And conversely, if you increase your speed just a little bit, your stopping distance increases by quite a lot. It goes up by the square of that value there. I hope this helped you to understand how to use some of these motion equations. They can seem quite intimidating. Look to the next few videos to see the motion equations in use for more difficult questions.